Today we'll be discussing on the topic of DC motor. I am Joshua Daniel, Assistant Professor, Department of Electrical and Electronics Engineering, Hindustan College of Engineering and Technology. Before we discuss about the principle of operation of a DC motor, we need to know some basic rules like the Maxwell's corkscrew rule, right hand thumb rule, which tells us in which direction the flux lines will be around a conductor when a current flows in a conductor. Next, we'll be seeing the Fleming's left-hand rule, which tells us in which direction the force acts on the particular conductor when it is placed in a magnetic field. Then we'll see what is a DC motor, how its operation, and what are the different types of DC motor. So what is a DC motor? A DC motor is a direct current motor which converts electrical energy into mechanical energy. When we see a DC motor, it is a fairly simple electric motor that uses electricity and a magnetic field to produce torque. Torque is nothing but a turning effect or twisting moment, which turns the rotor and hence gives mechanical work. So the input to a DC motor is electrical energy and the output is mechanical energy, which is nothing but rotation. When a current carrying conductor is placed in an electric magnetic field, it experiences a force. And that force is otherwise called as Lorentz force. Due to this force, you have the torque or the turning effect or the twisting moment. As you can see here, there is a conductor or two sides of a coil, right? In one side, the current enters the coil, and on the other side, the current leaves the conductor in that coil. So you can see that the conductor, one side is towards the south pole, the other side is towards the north pole. So what happens to the force on that particular conductor is explained clearly by Fleming's left-hand rule. In Fleming's left-hand rule, when we keep the index finger in the direction of the magnetic field and the current is denoted by the middle finger and the force on that particular conductor is mentioned with a thumb. If these are kept in right angles, that is 90 degrees to each other, you can know what happens to the force on that particular conductor when the current flows inside the conductor and when the current flows outside the conductor. Or you can say that the current is entering and the current is leaving. So Fleming's left-hand rule says that when a current carrying conductor is placed in an external magnetic field, the conductor experiences a force which is perpendicular both to the field and the direction of the current flow. As you can see, the current is entering here, the magnetic field is in this direction, right? And the current flows through this conductor in this direction. So you can see that the force is acting upwards, right? This is what the Fleming's left-hand rule tells us. Next, we need to see how the flux lines around a conductor is when current flows through a conductor, right? Corkscrew rule tells us that when it is pushed into a surface or it is screwed into a surface, right? The direction of the screw can be compared to the direction of the current, and the rotation, that is clockwise direction, is compared to the direction of the magnetic flux, right? Similarly, the right hand thumb rule, as you can see, if you are catching hold of a conductor, right, the thumb denotes the direction of current and the fingers here shows the direction of magnetic flux lines. So this is how you can know in which direction the flux lines are around a conductor when the current enters or when the current leaves a conductor. Next, let's see the principle of operation of a DC motor. As you all know, just now we saw that when a current leaves the conductor, which is placed in the armature slot, right? What happens to the force on that particular conductor? It acts upwards. How do you say upwards? It, it is due to, or it is proved with the help of Fleming's left-hand rule, right? Again, you can see in the second diagram, when the current enters the conductor, which is placed in the armature slot, what happens? This is the middle finger shows the current entering the conductor. So you can see the thumb shows the motion on that particular conductor. It is moving downwards, or it acts downwards, right? Next, let us see what happens to a current carrying conductor. So see, if the conductor is denoted with a dot, you can say that the current is leaving the conductor, right? So that flux around that particular conductor is in anti-clockwise direction, and it is placed in the main magnetic flux. So the lines in the main magnetic lines are from north pole to south pole. So when you analyze what happens above the conductor and what happens below the conductor, you can see above the conductor the flux lines oppose each other. So weakening of flux takes place here. But when you see in the bottom of the conductor, the flux lines aid each other. So what happens? Strengthening of flux takes place here. So obviously it tries to push the conductor upwards, right? So when you see the next diagram, you can say that the force is exerted on the conductor placed in the armature is downwards. Why downwards? See, a plus sign marks the current is entering the conductor. So the flux lines around the conductor is in clockwise direction. So above the conductor, the main magnetic flux and the flux around the conductor aid each other, and thereby it is strengthened on the above the conductor. And below the conductor, the flux lines are opposite to each other, so they cancel each other. Obviously, the conductor is pushed downwards, or the force acts downwards. Now, let us consider a coil which is placed inside a magnetic field. The coil is nothing but it is uh, wound on the armature, right? So, in one side of the conductor, the current enters, the other side of the conductor, the current leaves. So, the current entering clockwise direction, flux lines, and the current in the conductor where the current leaves, the flux lines are in this anti-clockwise direction. When this is placed in a main magnetic flux, what happens? You can see the next diagram. See, these are the slots in the armature, and in one side the current enters, and on the other side it leaves. So you can see the conductors which are near to the north side experience a force upwards, because below the conductor, all the conductors here experience a force upwards, because below these conductors the strengthening of flux takes place. But when you take the case on the right hand side, that is all the conductors in the right hand side, that is near to the south pole, the force or the strengthening of the flux takes place on the upper side, which tries to push the conductors down. So as a matter of fact, so what happens is all the conductors on the right side are pushed downwards, all the conductors on the left side are pushed upwards. So ultimately what happens is a turning effect or a twisting moment, or what we call as torque, sets up in a motor. The only thing what we are doing is we are placing a current carrying conductor in a magnetic flux or in a magnetic field, thereby it experiences a force. So we are just giving electrical energy to the motor. The electrical energy is present in the conductors, right? And when these conductors, or when this armature is placed inside a magnetic field or the field winding, right? As you can see in the very first diagram, I just want to, yeah. So what happens? Torque is set up. So this is the principle of operation of a DC motor. So you have two parts, one is the armature and another one is the field. When this armature or when this conductor which is in the armature is placed in the magnetic field or the field, what happens is it experiences a rotational torque. So we are giving electrical energy and it is converted to mechanical energy. So this is the principle of operation of a DC motor. So next, let's see the different types of DC motor. We have shunt motor, series motor and compound motor. What are these? So depending on how the armature winding and the field winding are connected to each other, it is termed as shunt motor or series motor or compound motor. Here you can see the shunt winding or the field winding is parallel to the armature. So it is called as a shunt motor. Excuse me. So the voltage is constant for both the armature as well as the field. So you can say that the flux is constant, thereby the speed is constant. For any application where the speed is constant, you can use a shunt motor. Next, let's see the series motor. When the armature and the field are connected in series, it is called as a series motor. Here, the flux depends on the change in current, right? So the current always changes here. So the speed also changes proportional to the current. So these type of motors have very high starting torque and it's always needed to be kept under loaded condition. So one of the application is traction, where you need high torque to start the engine to move the particular cage in a train. Next, if you need both the characteristics, we go in for DC compound motor, which is otherwise again subdivided as long shunt compound motor and short shunt compound motor. And depending on whether the fluxes in the series winding and the shunt winding oppose each other or aid each other, they are classified as cumulatively compound and differentially compound. Right? Let us see a long shunt compound motor. When the shunt winding is connected across the series winding as well as the armature, it is called the long shunt compound motor. If the long shunt winding or the parallel winding is connected only across the armature, it is called as a short shunt compound motor. If you need good starting torque as well as constant speed characteristics, you can go in for this motor, right? So based on, as I already told you, if the series winding flux and the shunt winding flux aid each other, it is classified as cumulatively compound, and if it opposes each other, it is differentially compound DC motor, right? So let's see the different applications of a DC shunt motor, series motor and compound motor. As I already told you, a shunt motor is a constant speed motor, so it is used in lathes, fans, pumps and wherever moderate torque is required. When we take in the case of series motor, it is used in electric traction and high speed tools. And in the case of DC compound motor, it is used in rolling mills and other loads which require large momentary torques. So hope you've understood the different rules that govern the operating principle of a DC motor and how it operates, what is Fleming's left-hand rule, how torque is set up in a DC motor, what are the different types of DC motor and where it is applied. Thank you for watching. Thank you for watching this video. Thank you.